This week we're going to be talking about batch effects and how to adjust for them. Now, to understand why batch effects are a problem, we're going to start discussing confounding. Explain what it is, explain how it could affect your bottom line results. So I'm going to give you an example. It's a very famous example of how confounding can confuse you if you're not careful in analyzing the data. This comes from admissions data from UC Berkeley in 1973. The university was being sued for gender discrimination, and the evidence for it was this. Basically came down to this table. So if you look at this table closely, you're going to see that while 45% of males were being accepted into graduate programs, only 30% of females were. Here we can do a chi-square test, as we learned in previous modules, to find that this discrepancy such as this is very unlikely to happen by chance if gender and admissions are in fact independent of each other. Now, when we look at the data a little bit more carefully, we see something that appears to be a paradox. If we split this data by major, so there's 6 majors, you're going to see that the admissions rates are about the same, and in fact it appears to favor females. For example, major A clearly favors females. So how can this possibly be happening? We have at each major the admissions slightly favoring females, but as an aggregate the admissions are clearly favoring male. So to understand why that happens, we have to understand what confounding is. In this case, we have that the number of applications is confounded with admissions rate, especially for males. So it turns out that males were more likely to apply to quote-unquote easy majors or easy to get in majors than females. So it appeared that they were being admitted more often, when in fact what was happening was that they, by their own choice, they were applying to the easier majors. And you can see it in this picture. If you look at the ones, those are the males. On the x-axis, we have the percent that get into the major. So this is a major that's a little bit easier to get into than this one, well, more than a little. And then this, on the y-axis, we have the percent of admissions that went to that major. So you can see very strong association between the admissions rate of a major and the total number of applications or percent of applications for males, but we don't see that pattern for females. So to sort of very clearly see this, I'm going to show you this data in graphical form. In this plot, I have every person is represented by a little dot. If you look closely enough, you're going to see that there's A, B, C's, D's, E's, and F's. Those are the majors. And the colors represent green means you got in, you got admitted, and orange means you didn't. So when we look at it like this, when we put all the majors together, it's clear that males are admitting more often. You can see there's much more, as a percent, there's much more green than orange in the male side of the graph than in the female side of the graph. But now we're going to take the same data, these same individuals. We're not going to add any, we're not going to take any away. All we're going to do is reshuffle them by their majors, which is already done by the letters, the symbols, but now we're actually going to split them up, stratify. Stratification is a powerful way of finding confounders. So once we stratify, if we go major by major, you can see that there does not appear to be any gender bias. Every single one has about the same rate of admissions. Now, where you can see a humongous difference is in these majors. These are the majors with a lot of green. Those are, again, quote-unquote, the easy majors to get into. And in those 2 rows, you can see which of the 2 genders is applying more. So this fact that you have so many men applying to these 2 majors explains why you see more green here than here. Again, it's confounding. It's not, in this case, bias coming from the admissions office. It's confounding with the fact that males were applying to the easy majors. So as we just said, one way of parsing this out is by stratifying. And here we can see the proportions that are admitted by major. So if you want to compute, if you want to see if there's a difference, you should compute the difference at the level of major, right? So you stratify, then compute differences. And if we do that, if we compute the difference between males and females in each one of these and take an average, we see that they're roughly admitted at the same rate. In fact, women are on average have a 3.5% higher rate. So this is a very, very famous example of confounding. It's very commonly used to explain it, but it shows up in other instances. Here's another case from baseball. And in this case, what I'm showing you is if you look at, this is data, batting averages for Derek Jeter and David Justice. In 1995, that was Jeter's first year. In 1996, if you look at their batting averages in these 2 years, both years, David Justice had a higher batting average than Jeter. Both years. But in the combined, if you combine these 2 years, Jeter has a much higher batting average than David Justice. So how is that possible? Again, it's confounding. Jeter batted fewer times in 1995 when he had a lower batting average, and he batted many more times in 1996 when he had a much higher batting average, while the opposite is true for David Justice. So once you aggregate all that up, you see that combined, Jeter is the better hitter. So we're going to see that confounding shows up in genomics data, and it causes a lot of trouble if you don't realize that you have it and if you don't adjust for it. And we're going to do that in the next modules.